In this lecture, we are going to discuss statistical testing, which ties in nicely with two things we previously discussed. Earlier, we looked at how to check if our data was actually coming from a normal distribution by using a QQ plot. This was a graphical method of checking whether or not your data comes from a certain distribution. Statistical testing offers a quantitative way of doing the same thing. In addition, we'll see how statistical testing follows directly from our discussion of confidence intervals. Before we get into any theory, I want to discuss the API approach to statistical testing. This approach might be thought of as the lazy approach, the beginner's approach, or just an approach for people who don't like math or whose main field is not statistics. For these people, the process is quite straightforward. The basic API of a statistical test is like this. You start out with what's called the null hypothesis. It's helpful to use examples, so let's suppose you are a drug company and your job is to test whether or not a drug is working. Typically in these experiments, you have two groups of people. One group of people is called the control group, and one group of people is called the treatment group. The control group receives a pill which is called a placebo. Typically, this is just a sugar pill. This has no medicinal effect. The treatment group receives the actual drug you want to test. Your data will consist of some measurement which is related to the intended effect of the drug. For example, if it's a drug to lower blood pressure, then your data would be a measurement of the patient's decrease in blood pressure after taking the drug. Alright, so what's the null hypothesis? The null hypothesis would be that the drug has no effect. We typically use the symbol H0 to express the null hypothesis. The alternative hypothesis would be that the drug does have an effect. We typically use the symbol H1 or HA to express the alternative hypothesis. After consulting with your colleague about the correct statistical test to perform, you then call that function in your code. The output is what is called a p-value. The p-value is a probability. We'll discuss what it means later, but for now, this explanation is for the beginner approach only. If the p-value is less than some threshold, then we reject the null hypothesis. Typically, this threshold is set to a value like 5% or 1%. If the p-value is greater than this threshold, then we do not reject the null hypothesis. In our example, a p-value less than 5% would indicate that there is a significant difference between the treatment group and the control group. If the p-value were very large, say 90%, typically the way this would look in the data is that there would be a large overlap between the treatment group and the control group's measurements. In other words, the difference between the treatment group and the control group is not significant. Note how there's a subtle use of language here. If this were machine learning, we would usually speak in more concrete terms. For example, I classify this picture as a dog, or I classify this picture as an airplane. But we don't say things like, I reject that this picture is a dog, or I cannot reject that this picture is a dog. Such statements would be quite silly. However, that's exactly what we do in statistics. We don't accept the alternative hypothesis, we only reject the null hypothesis. Furthermore, if we get a p-value which is very high, like 90%, we especially do not accept the null hypothesis. Sometimes people will say they accept the alternative, but they would never say that they accept the null. We can only fail to reject the null hypothesis. So just keep this in mind when you're talking with statisticians who tend to be extremely precise when discussing these kinds of things. You either reject or you fail to reject, but you do not accept. Practically speaking, at the end of the day, you do have to decide that the drug works or not. So it does seem quite silly that you'll never make a statement like, this drug works. Practically, that's what you're doing, but you prefer to say, I reject that this drug does not work. Let's now try to understand what we are doing in a graphical way. The previous example I gave you is called a two-sample test. That's because your control group is considered one sample, and your treatment group is considered the other sample. You can imagine that your measurements from each group gives you two separate bell curves. Of course, there might be some overlap. For example, if you're measuring the heights of men and women, of course there are some women who are taller than some men, so there is some overlap between the two groups. However, the difference in height between men and women is significant. So what a statistical test is trying to do is tell you whether these two bell curves are significantly different. A naive approach might be to look at this and say, well, why can't I just take the sample mean of each group and compare them? If the sample mean of the treatment group is larger than that of the control group, then the treatment works. Of course, that does not account for statistical flukes. Think of an extreme example where your control group only has one person and your treatment group only has one person. If you only compare sample means, then one group's mean must necessarily be larger than the others. So if the control group has mean 0.001 and the treatment group has mean 0, that doesn't necessarily mean that the treatment makes your condition worse than the control. In fact, this doesn't account at all for the fact that the treatment might have no effect. Depending on the variance and sample size, it may simply mean that there is no detectable effect. So the two-sample test is nice for intuition, but the one-sample test is nicer for understanding the mathematics. The one-sample test is even simpler than the two-sample test. In this case, I only have a single group of measurements, and what I want to do is compare them to a single number. This is opposed to the two-sample test, where I want to compare the two groups of measurements to each other. For example, suppose I want to compare the scores on a standardized test for my school compared to the national average. Graphically, what I want to do is draw a bell curve representing the distribution of the sample mean of the test scores, along with a point representing the national average. The national average will be called mu naught, and the average test scores at my school will be called x bar, whose true mean is mu. Note that when doing these tests, it's clear that scale has to matter. For example, I shouldn't get a different result if my scores are out of 100 or if they are out of 1000. Well, it turns out that this is nothing but our confidence interval. The way that a statistical test works is like this. Suppose that my null hypothesis is that mu is equal to mu naught, and my alternative hypothesis is that mu is not equal to mu naught. Remember that mu is the expected value of my school's test score. Another way of asking this question is to look at, what is the confidence interval for mu? Remember that there's 5% of probability mass that I want to consider highly improbable. That's 2.5% on the left and 2.5% on the right. If this mu naught falls into either of those regions, either on the extreme left or the extreme right, I will reject the null hypothesis. This area where I can reject the null hypothesis is called the rejection region. Conveniently, I can calculate the boundaries for this rejection region in exactly the same way that I calculated confidence intervals. In fact, if I take x bar, subtract mu naught, and divide by the standard deviation in order to normalize the test scores for scale, this is exactly the expression we had before for the confidence interval. As you've seen, the rejection region after doing this standardization is minus 1.96 and plus 1.96. Therefore, I first calculate x bar minus mu naught, divided by sigma over the square root of n. We'll call that z. By the way, this z is called a test statistic. Then I check whether or not z is bigger than 1.96 or less than minus 1.96. If it is, I reject the null hypothesis that mu is equal to mu naught. This test is called the z-test. Using this picture, we can now discuss the meaning of the p-value. The p-value is just the probability of seeing a result as extreme or more extreme than what we observed. In other words, suppose that I did see a very extreme result, and therefore reject the null hypothesis. Suppose that my test statistic lies at minus 2. The probability of seeing something as extreme or more extreme than minus 2 is the probability that the test statistic is minus 2 or less, or plus 2 or more. So we have to account for the area under the curve in both tails. This is called a two-sided test because when our null hypothesis is that mu is equal to mu naught, the alternative is that mu is not equal to mu naught. That means mu could be greater than mu naught, but also it could be less than mu naught. The way that we calculate this p-value is to take 1 minus the CDF of the absolute value of z, where z is the test statistic, and then multiply that by 2 to account for both sides. We take the absolute value to account for the case where z is negative. You might want to work this out on paper to confirm that this is correct. A similar test, which is probably of more practical significance in our case, is the one-sided test. For example, suppose we want to know whether or not our treatment improves clinical outcomes. This is different from, say, comparing the standardized test scores from my school, because if my test scores are worse than the average or better than the average, either way I would consider these significant results. To bring this back to finance, it's easy to see how this can apply. Another example for stock returns is that I want to know if my returns are significantly greater than 0. If they are less than 0, I don't care. I can simply choose a different stock. Now, when you're testing multiple things at the same time, you have to be careful, but that's outside the scope of this lecture. In this case, the null hypothesis is that the expected return is less than or equal to 0. The alternative hypothesis is that the expected return is greater than 0. In this case, if our significance threshold is 5%, the entire rejection region is located on a single side of the distribution. The p-value will be significant if the test statistic is beyond this threshold. To calculate the p-value, it's just 1 minus the CDF of z, where z is the test statistic. Note that this is half the value of the two-sided test. Therefore, if you have a library that only offers two-sided tests, you can simply divide the p-value by 2. But note that this formula only works if you're checking the greater than case as your alternative hypothesis. You could rederive this for the less than case if you wanted. One final note for this lecture is that this was to build your intuition only. As you recall, we don't actually know the true sigma, and therefore we have to estimate it using the sample standard deviation. When we do this, our test statistic becomes t-distributed rather than normal. So in actuality, one would use the t-test rather than the z-test. Furthermore, note that the t-test makes the assumption that your data is normally distributed. But again, many people often use the t-test as an approximation anyway, just as they do for confidence intervals. Finally, note that we will be discussing all kinds of statistical tests in this course. What we just looked at is a simple example that's very easy to draw a picture of. Of course, we're not going to have time to derive them all. In the coming lectures, we'll be looking at tests for whether or not our data comes from the normal distribution or any distribution in general. Specifically, the Jark-Barrett test can be used for testing normality. For this test, the null hypothesis is that the data is normal, and the alternative hypothesis is that the data is not normal. So if you reject the null hypothesis, you're saying that the data does not look like a normal distribution. Another test in SciPy is simply called the normal test, which does the same thing. Again, the null hypothesis is that the data is normal, and the alternative is that it's not. Finally, we will use the Kolmogorov-Smirnov test, which can test for any distribution. Again, the null hypothesis is that the data does come from that distribution, and the alternative is that it does not. Finally, I just want to reiterate that in this course, understanding the mechanics behind statistical testing is mostly optional. I could make an entire course on this subject, and in fact, I have. We'll be looking at lots of tests in this course, and we will definitely not have time to explain them all in detail. Therefore, it's sufficient to just understand the API of a hypothesis test. As input, we have our data, we have a null hypothesis, and we have an alternative hypothesis. As output, we get a p-value, and optionally, the test statistic associated with that p-value. We check the p-value against a significance threshold. Typically, we're going to use 5%. If we get a p-value below 5%, we'll say that the result is significant, and we will reject the null hypothesis. Otherwise, we will fail to reject the null hypothesis.